Welcome to an exploration of why Rust's approach to concurrency is truly groundbreaking. In a world where parallel processing is the norm, Rust ensures safety and performance without the typical risks. By integrating a stringent ownership system, Rust eliminates data races, offering developers confidence in their code. This capability is vital as applications increasingly demand robust, high-performance solutions. Let's delve into how Rust achieves this remarkable feat. Now that we understand Rust's strengths, let's dive into the common pitfalls faced in traditional concurrency. In many languages, data races occur when two or more threads access shared data simultaneously without proper synchronization. This often leads to unpredictable behavior, making debugging a nightmare. Deadlocks present another headache when two or more threads become locked, each waiting for the other to release resources, freezing progress entirely. Without Rust's ownership guarantees, these issues can wreak havoc on software reliability. After exploring traditional pitfalls, let's dive into how Rust tackles concurrency with a unique model. At the heart of Rust's approach are its ownership and borrowing concepts, which prevent common data races by ensuring single ownership and controlled access. Then there's the send trait, marking types that can be transferred across threads, and the sync trait, allowing shared data access safely. These mechanisms work harmoniously to provide safe and efficient concurrent programming. Now that we understand Rust's approach to concurrency, let's see it in action with some live coding. We're going to manage multiple threads and safely share data using the mutex and arc constructs. In this example, we create a counter that 10 threads will increment concurrently. Each thread locks the counter, increments its value, and then releases the lock. By utilizing arc for atomic reference counting and mutex for mutual exclusion, we ensure that our counter updates are safe and free from data races. This example highlights Rust's powerful concurrency model in practice. In our previous example, we saw how to use mutex and arc to safely share data across threads. Now, let's explore best practices to enhance your Rust concurrency skills further. First, aim to minimize shared state. This reduces the complexity and potential for error in your applications. Secondly, embrace immutability where possible. Rust's safety principles align well with immutable data, as it naturally eliminates many concurrency issues. Finally, leverage channels for communication between threads. Channels can be a powerful alternative to shared state, providing a clean and safe way to transfer data. Remember, always be cautious of overusing locks, as they can lead to performance bottlenecks if not managed carefully. As we wrap up, remember that embracing Rust's concurrency model can dramatically enhance your software's safety and performance. By applying the principles of minimizing shared state, leveraging immutability, and using channels, you can tackle complex concurrent programming with confidence. Implement these strategies in your projects and see the difference they make. We hope this guide has empowered you with the knowledge to master Rust concurrency. Don't forget to like, subscribe, and share your experiences or questions in the comments below. We'd love to hear how you're applying these techniques.